Welcome, everyone. For today's prep, we're going to be looking at tangent lines. And this is really going to be our introduction into the idea of derivatives. So something we're going to be spending quite a bit of time on. So this is going to be the conceptual idea for what we're going to be doing when we later on calculate derivatives. So for this lesson, we're going to see how to calculate the slope of a secant line, and actually what a secant line is. We're going to see how to actually calculate the slope of the tangent line, and then how to actually get the equation of the tangent line at a specific point. All right, so we're going to be talking about lines. So let's just review a few basic formulas. So if we have a line, and we know 2 points on that line, we can figure out what's called the slope of the line. And the slope of the line essentially is the change in y over the change in x. So we take the y coordinate from point Q and we subtract off the y coordinate from point P. And then we do the same for the x coordinates. So the x coordinate from point Q minus the x coordinate of point P. So the only thing, the order doesn't matter too much in how we do the subtraction here, as long as we're consistent. So if we start with the coordinates from point Q, they have to go first. They both have to go first. And again, we can think of the slope here as really change in y over change in x. And sometimes we abbreviate this with delta. So we might say like delta y over delta x. Change in y over change in x. All right, so in order to find the slope of a line, we need to know 2 points. Once we have the slope, then we can use one of those points to actually figure out what the equation is for our line. So in order to get the equation for a line, we need to know 2 things. We need to know the slope, and we need to know the point. And the point slope formula, this is the one we're primarily going to be using, is y minus the y coordinate of our point set equal to the slope times x minus the x coordinate. And you can kind of remember this formula by just dividing both sides by the x minus the x coordinate, and then we have, essentially the formula for slope. Now the difference here is in this equation, the y that we see here and the x that we see here, these are variables. So when we write down our equation, normally we're going to have x's and we're going to have an x and a y term in it. So these should be variables here. And then the rest of these should just be constants. So the y coordinate, the slope, and the x coordinate, those should all be constants, numbers. All right, so just some basic formula that we're going to be using. So we want to get into the discussion. We want to find the equation of a tangent line to a curve. And kind of a way of introducing what a tangent line is with circles, because this is where we actually have ways of constructing the tangent line to a circle. And we have some idea of what a tangent line should do when we're talking about circles. So in our little example here, we have a circle here. We have our point that we're interested in, and we've drawn the tangent line. So for a tangent line, the idea with a circle is the tangent line should just barely touch the circle. It should only intersect the circle at that one point. So like I said, when we're dealing with circles, we have geometric ways to actually construct this line and get it. All right, so what are some important characteristics that our tangent line and our circle, well, the tangent line for our circle should have? So there's a few of them. So first of all, it should just barely touch the circle at that point P. And we kind of see that here. So we just kind of imagine this tangent line just grazing the side of the circle so that it only intersects at that one specific point. Another kind of characteristic is that when we get really close to point P, the circle and the tangent line should kind of look very similar. The tangent line should be a good approximation of the circle at that point P. So if I were to zoom in on this section of the circle, and that's what we're seeing here, we're just kind of zooming in. Once we get close enough to point P, you can't really tell where the circle is and where the actual tangent line is. They look very similar right around that specific point. And kind of another characteristic, similar to the second one here, is that if we're traveling around this circle, so imagine a little particle moving around this circle here, and a particle moving along this line. Once the particle gets to that point P, and once it gets to point P on this line, it's kind of traveling in the same direction. So at that point P, the tangent line and the circle, they're kind of going in the same direction. So the tangent line and the circle should have the same direction at point P. All right, so how do we extend this idea to not just tangent lines for circles, but how do we do this for general curves? So there are ways to actually construct the tangent line for a circle, but how do we actually construct it for a general curve? And so this is going to present an issue. So on our little diagram here, we're going to have a function y equal to f of x. So here's our curve. And we want to construct this tangent line. So here's our tangent line at some point P. How do we do it? Well, the difficult thing with constructing a tangent line or knowing the equation for a tangent line for a general curve is, in order to get the equation for our tangent line, we need to know two things. We need to know the slope, and we need to know a point. So we need to know the slope m, and we need to know a point. Call it x coordinate, y coordinate. Those are the two things we need for any equation for a line. So in particular, for a tangent line, we need to know the slope of the tangent line, and we need to know the point that's on the tangent line. Well, we have our point P. So we have the point. So knowing the point is not the issue. We have our point. The issue really comes down to the slope. So in order to figure out the slope of a line, in general, we need to know 2 points that are on the line. We only know one. So that's the issue. So we only know 1 point on our tangent line. So if we go back, why is it a problem that we only know 1 point that's on our tangent line? Well, if we go back to our slope formula requires 2 points. So where do we get the second point from? Well, we're going to kind of sneak up on it. And that's the idea of how we're going to construct our tangent line. So how are we going to do it? Well, we're going to pick a second point Q somewhere else on our curve, kind of close to point P, but not exactly point P. So we have our point P. This is the point where we're interested in drawing the tangent line. We're going to pick a point Q somewhere off a little bit. And we draw a line connecting those 2 points. That's a secant line. So it it goes through our curve twice, 2 distinct points. So that's not the line that we want, because this really isn't doing the job of our tangent line. It's not just barely touching our curve. Our curve and our tangent line here are going in the same direction, but the curve and the secant line, they're not really going in the same direction. And if you were to zoom in on this section here, we have our curve, and then right around our point of tangency, that tangent line and the curve should look very similar, whereas with the secant line, there's a clear difference. So the secant line alone doesn't do it. So then the next step is we're going to calculate the limit of the slope as point Q moves closer and closer to point P. And so we're going to move point Q closer and closer to P. So that idea of moving something closer and closer, that's our whole discussion with limits. So that's why we've been talking about limits, is we need some kind of mathematical way to talk about taking a point, moving it closer and closer to another point. So let's see this in action. So let's see this construction in action. So a little animation here. All right, so we got our curve, and we're going to watch as point Q moves closer and closer to point P. And notice that secant line is getting more and more like what we want our tangent line to be, until once Q gets super, super close, the secant line is looking very, very similar. And so once we reach that logical conclusion, once we see where the limit's taking us, we have our tangent line. There we go. Look at that. So getting closer and closer, point Q's just kind of sliding along the curve, and then once it reaches its logical conclusion, we have our tangent line. So let's look at our formula. So how we're going to actually find the slope of our tangent line. So we're going to have two formulae to consider. One of them is easier to kind of see where it comes from. The other one's going to be better for calculations. So here is the slope formula for our tangent line. So M here, this is the slope of our tangent line. And like I said, we're going to have two different formulas that we can use. They're equivalent. They'll give us the same answer. But, one's better for certain aspects and the other one's better for others. So we'll see that later on. All right, so let's look at this one. This is the one we're going to look at right now. Limit as x approaches a of f of x minus f of a all over x minus a. All right, so let's look at a few things here. Let's look at first this fraction. What does this fraction represent? Well, this fraction, let me use green. This fraction, this is the slope of our secant line. All right, so let's see where this comes from. So let's pop over to our graph here. So here we go. And again, we have our curve, y equals f of x, and then we have our secant line, which we draw. So we pick that second point Q, and we have our point of tangency, we have our point Q, and then we draw the line connecting those 2 points. All right, so what are the coordinates for point P? Well, usually we're going to be looking at some kind of specified point. So we're going to call the coordinates for point P here a comma f of a. So the x coordinate is, we're just going to, some constant a. And the way we figure out the y coordinate for this point is we just take the x coordinate and plug it into our formula. And that gives us the y coordinate. Well, X is the thing that's going to be moving around. So we're going to let, spoiled it. Q is the thing that's going to be moving around. So that's the thing we're going to leave as a variable. So A here is just a constant. It's some kind of specified number that we're looking at. And Q is the thing that we're going to be moving around our curve. So we want that as a variable. So we're going to call that X, and then to get the Y coordinate for our point, f of X. We just take the X coordinate and we plug it into the function, and that gives us the Y coordinate. All right, so now we have 2 points, and we have a line connecting those 2 points. So the way we get the slope for that secant line is now we just go back to that original slope formula that we had, and we do change in y over change in x. So we're going to take our y coordinate for point Q, subtract off the y coordinate for point P, and then do the same thing for the x coordinates. So our y coordinate for point Q is f of x. The y coordinate for point P is f of a, and we subtract. And then the x coordinate for point Q is just x. And then the x coordinate for point P is a. So this f of x minus f of a over x minus a, this is just the slope of our secant line. And then when we take the limit of this as x approaches a, that's us moving point Q closer and closer to point P. Now sometimes, and we'll look at this more in class, but sometimes it's easier if we do a slight change of variables, and rather than talking about x, we're going to let x equal a plus h. So h is kind of how far away we are from how far point Q is along the x-axis. So it's kind of where x equals a, but then we're adding a little bit extra to get our point Q. So if I were to take a plus h and plug it in for the x there, I get a plus h. And then if I were to plug in the a plus h here, I'm going to have a plus h minus a, which is just going to leave me with an h. And then as x approaches a, really what's happening is point Q is getting closer and closer to point P. So h again is kind of how far apart those two points are. So h goes to 0. So really what we're doing here by getting the slope of our tangent line, we're figuring out the slope of our secant line, and then we're watching what happens. We're calculating the limit as that second point gets closer and closer to our point of tangency. So just a little practice. We're going to look at example, we're just going to do part A here. We're going to find the slope of the secant line. So we have this parabola y equals x squared. We have this specified point P with coordinates 1, 1, and we're going to find the slope of that secant line where point Q, this second point, has coordinates 2, 4. So what is the slope of the secant line in this case? So we'll call this MPQ. Well, again, it's the y coordinate of point Q minus the y coordinate of point P divided by the change in x. And again, the order doesn't matter here as long as we're consistent. So I have the coordinates from point Q first. All right, so what's our y coordinate from point Q? Well, it's 4. And what's our y coordinate from point P? It's 1. And then x coordinate from point Q? Well, it's 2. And then our x coordinate from point P is 1. So if we calculate this, we end up with 3 over 1, change in y over change in x, just positive 3. All right, So we're going to get a little practice with this in class in, calculating secant slopes of secant lines where maybe we're picking a second point that's a little bit closer. And then ultimately we're going to see how do we get that slope of the tangent line. But we'll see that in class. All right. So we'll see you then. Bye-bye.